Welcome to the sixth session of this Functions and Relations series. In this session, we will explain function transformations and the use of matrices to achieve the same transformations. We will summarize and demonstrate transformations of dilations, reflections, and translations through 8 worked examples. Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the sixth session of this functions and relations topic. Through this session, we are going to introduce the function transformation, as well as how to use matrices to achieve the desired transformation through 8 worked examples. Here are 3 commonly used transformations: dilations, reflections, and translations. And we're going to take a close look at these transformations. As for dilation, the point x, y, dilated by factor a parallel to y-axis or from x-axis, the coordinates of the point becomes xay. The point xy, when dilated by factor b parallel to the x-axis or from the y-axis, the coordinates becomes bxy. The next one is the reflection. When the point xy is reflected in the x-axis, it becomes the point x negative y. When the point xy is reflected in the y-axis, it becomes the point negative xy. As for translation, the point xy, when translated h units in the positive direction and translated k units in the negative y direction, it becomes x plus h, y minus k. All of the transformations that we have shown just now can also be achieved by using matrices. Let x prime y prime be the image of x, y. The following is a summary of the various transformations of dilations, reflections, and translations. When dilated by factor a parallel to the x-axis, the first row of the transformed matrix becomes ax, while the second row remains unchanged. When dilated by factor b parallel to the y-axis, the first row of the transformed matrix remains unchanged, while its second row of transformed matrix becomes by. As it can be seen, when reflected in y-axis, the first row of the transformed matrix becomes negative x, while the second row of the transformed matrix remains unchanged. When reflected in x-axis, the first row of the transformed matrix remains unchanged, while the second row of the transformed matrix becomes negative y. When reflected in the line y equals x, the first row of the transformed matrix becomes y, while the second row of the transformed matrix becomes x. When translated h units in the x direction and k units in the y direction, the first row of the transformed matrix becomes x plus h, while the second row becomes y plus k. Example 1 shows a function of y equals x raised to the 4th, which undergoes the following transformations: dilated by factor 3 from the x-axis and then translated 1 unit in the negative x direction and 1 unit in the negative y direction. The question is to find the equation of the transformed function. To answer this question, we use a 2 by 2 matrix to represent the dilation and a 2 by 1 matrix to represent the translation parallel in x and y axis. Here x prime and y prime represent the coordinates of the transformed function. After simplifying the right-hand side of the matrix equation, we have established the relations between the coordinates of the original function and the coordinates of its image. Since x equals x prime plus 1 and y equals y prime plus 1 over 2, hence the transformed function is y prime equals 2 times x prime plus 1, or in parentheses raised to the fourth minus 1, which is equivalent to y equals 2 times x plus 1, or in parentheses to the fourth minus 1. In example 2, the original function is a cosine function. The question is to show the transformed function with the following transformation: reflected in the x-axis, dilated by factor half, parallel to the x-axis, translated pi over 2 units in the positive x direction, and 3 units in the negative y direction. To answer this question, we set up the matrix transformation for the reflection in the x-axis, followed by the matrix transformation by a dilation factor of 2 parallel to the x-axis. Then we add the translation matrix of pi over 2 units in the positive x direction and 3 units in the negative y direction. After expanding and simplifying the matrix equation, we have 2 simultaneous equations established: x prime equals half x plus pi over 2, and y prime equals negative y minus 3. Based on the reflection between x and y, we can establish the relation between x prime and y prime. Finally, we have the transformed function of y equals cosine 2x minus 3. The original function in example 3 is that y equals square root x. The question is to write down the transformation matrix and thus find the transformed function given that the function is reflected in the y-axis, dilated by factor half from the x-axis, and shifted 2 units towards left. As we just learned, the matrix representing the reflection in the y-axis is a diagonal matrix with negative 1 at the first row and first column. The matrix representing the dilation by factor half from the x-axis also is a diagonal matrix with a half at the second row and second column. The translation of shifting left 2 units can be represented by a 2 by 1 matrix with negative 2 at the first row and 0 at the second row. Hence, we may write down the matrix equation and then find the relations between x prime and y prime through the relations between x and x prime as well as between y and y prime. Finally, we have the transformed function of y equals half times square root negative x minus 2. Example 4 provides a matrix transformation from one relation to another. The question is to find the image of the function, given that the original function is y equals 1 over x squared. According to the given matrix transformation, we have the simultaneous equations of x prime equals x minus 3, y prime equals negative 2 times y plus 1, or in parentheses. Hence, we can express x in terms of x prime and express y in terms of y prime. Therefore, the image of the original function under the transformation is that y equals negative 2 over x plus 2, or in parentheses squared minus 2. There are 2 functions in example 5. fx equals x squared, gx equals half times x plus 4 over 2, or in parentheses squared minus 1. The question is to create a matrix equation which would transform fx to gx. Now, according to the rule of fx and gx, we perform the transformation in a step-by-step manner. The first step is to apply a dilation factor 2 parallel to x-axis, which represents a value of 2 on the upper left corner of a 2 by 2 diagonal matrix, while the rule of the transform function becomes fx equals x over 2, or in parentheses squared. The second step is to apply a dilation factor half in y-axis, which shows a value half at the down right corner of the diagonal matrix. The corresponding transform the function now becomes half times x over 2, or in parentheses squared. The third step is to translate 4 units to the left, and the transformation is represented in a 2 by 1 matrix, where the translated value -4 is stated at the first row. The transformed function now becomes half times x plus 4 over 2, or in parentheses squared. The last step is to translate 1 unit downwards, which is represented by a value of -1, placed in the second row of a 2 by 1 matrix. Now, the transformed equation becomes the image function, gx. After arranging all the transformations matrices together, we have the matrix equation which transforms fx to gx as shown on the screen. Example 6 is to transform from fx to gx using matrix equation. Here fx equals 1 over x, while gx equals -2 over the result of 3x minus 1, then plus 4. According to the rule of fx and gx, we perform the transformation in a step-by-step manner. Not only do we show the function expression in each step, but also the expression in the transformation matrix. After dilation factor 1/3 being applied in x-axis direction, the function fx becomes 1 over 3x, and the corresponding matrix for dilation is also shown. The second step is to apply a dilation factor 2 in y-axis, which means to multiply the equation by 2. Accordingly, the equation of matrix transformation for a dilation of factor 2 parallel to y-axis is also set up as shown on the screen. The third step is to reflect in x-axis, which means to multiply the equation by -1, and the corresponding matrix transformation equation for the reflection is also shown. The fourth step of transformation is to move 1/3 units in the positive direction of x-axis, which means to replace x with x minus 1/3 in the matrix transformation equation. Accordingly, the translation of 1/3 units in the positive direction of x-axis is represented by adding a 2 by 1 matrix of the equation. The last step of the transformation is to move 4 units in the positive y direction, which means to add 4 units to the equation. In the meantime, the matrix transformation for the translation 4 units in the positive y direction is also shown by adding a 2 by 1 matrix in the equation. Finally, the matrix equation to transform fx to gx can be established by summarizing all the above transformations to form the equation of the image as shown on the screen. Example 7 shows a matrix transformation equation where constants of a, b, and c are non-zero real numbers. The question is to find the values of a, b, and c, given that the matrix equation transforms fx to gx. We herewith demonstrate 2 approaches for this question. The first approach is based on the rules of the function and its image. We will do the transformation in a step-by-step manner, and at the same time we will specify the transformation matrix for the corresponding transformation step. The second approach is to start from the given matrix equation and based on the rules of the function and its image to find the required constants. Now we have three steps to transform from fx to gx. The first step is to translate one unit in the positive direction of x-axis, which means in fx we replace x with x minus 1 and the corresponding translation matrix is also displayed. The second step is to translate 3 units in the positive y direction and we just add 3 to the equation. The third step, or the last step, is to dilate a factor 1/2 in y-axis, which means to multiply half to the equation. The matrix equation for such a transformation step is also shown. Based on the above, we have the matrix equation established to complete such a transformation. After simplifying the matrix equation and then make a comparison to the matrix equation shown in the question, we find the values of A, B, and C are 1/2, 1, and 3/2, respectively. Here we continue to work on example 7. According to the given transformation matrix, the right-hand side of the equation is expanded and we have x prime equals x plus b, while y prime equals ay plus c. Hence, we may express x and y in terms of x prime and y prime. Since fx equals 2 over x plus 1 minus 3, we substitute x with x prime minus b, substitute y with y prime minus c over a. After simplifying the expression of the image function, we compare it with the gx, which is 1 over x. Hence, we have 3 simultaneous equations established to calculate constants of a, b, and c. Finally, we have calculated the values of these constants and find a equals 1/2, b equals 1, and c equals 3/2. Example 8 shows a matrix transformation equation where constants of a, b, c, and d are non-zero real numbers. The question is to find the values of these constants given that the matrix equation transforms from gx to hx. We will demonstrate 2 approaches for this question. The first approach is based on the rules of the function and its image. Here we perform the transformation in a step-by-step manner. In each step, we will not only show the change of the rule, but also to demonstrate the corresponding matrix equation in regard to the transformation. However, for the second approach, we will start with the given matrix equation and establish the relations between the coordinates of the function and the coordinates of its image. Hence, based on the rule of the function and its image, we will find the required constants by using the coefficient equating method, which means when 2 equations are equivalent, their corresponding coefficients are the same. Now, the first approach. In the first approach, the first step of transformation is to translate 1/3 units in the negative x direction, which means to replace x with x plus 1/3 in gx. The corresponding matrix equation to perform the same transformation is also shown. For the second step, we translate 2 units into negative y direction, which means it subtracts 2 from the previous function. In the matrix equation, it adds a 2×1 matrix with -2 placed in the second row. The next step of transformation is to apply a dilation factor 3 parallel to x-axis, which replaces x with x over 3 in the function of the previous step. In the meantime, the matrix equation of illustrating such a transformation is also shown. The last step of transformation is the reflection in x-axis, in which we times -1 to the function from the previous step. Finally, we have the complete matrix equation of transformation, so we may compare it with the given matrix equation, and then apply the coefficient equating method. Hence, we find a equals 3, b equals -1, c equals -1/3, and d equals -2. Here we continue work on example 8. Now we explain the alternative approach to calculate these constants. According to the given transformation matrix with the constants a, b, c, and d, the right-hand side of the equation is expanded, and we have x prime equals a times x plus c, or in parentheses, while y prime equals b times y plus d, or in parentheses. Conversely, we may express x and y in terms of x prime and y prime respectively. Since gx equals -3x minus 1, or in parentheses squared, plus 2, we substitute x with x prime over a then minus c. Substitute y with y prime over b then minus d. After simplifying the expression of the image function, we compare it with the image function hx, which is x squared. Hence, by applying the coefficient equating method, we have 4 simultaneous equations established to calculate these constants. Finally, we have obtained that a equals 3, b equals -1, and c equals -1/3, d equals -2.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.